for connecting again with us to the webinar this week. Last webinar with Bob White, we were talking about our new tool, Frenetic AI version 3. And I would like to start talking a little bit about it. Our intention today is to share again the link with you so everybody can try the tool, and for us would be great to have your feedback. So Jonas, I don't know if we can have a quick view of the Frenetic version 3, and then we can explain a little bit the next updates we will have.
Yes, perfect. Yeah, I will show very quickly the tool. Let me share the screen. So, is that the right screen? Can you see now my screen at home? I hope so. Yeah, perfect.
Yes.
So, many of you might have already heard we work on Frenetic AI. That's a new layer that helps to design power converters. We now recently launched the version 3, which has a completely new look and feel. It looks much more neat than what we had before. The tool itself is basically the same. Now new, you can also save your projects. So start new projects, save projects. You start with your topology, and many more topology will come here. You put in your requirements and whatever else you like is important. Let's say if you want to enforce a switching frequency or something similar, you click one button, design a converter, and it calculates kind of all the components needed for this converter, like the resonance tank in this case of a full bridge LLC. You can then further have the tool to design a magnetic component. For this, we use our Frenetic magnetic simulator. It's calling an API there to get you a design. In this case, it's an integrated resonance inductor plus a transformer. As you can see here, you see all the information and so forth. Now here you cannot change a lot, but what you can do is open this design in Frenetic simulator, Frenetic magnetic simulator. So you have here the same information from before, and you can do further adjustments as we have shown already before. You can also download an LT-SPICE file. You click a button and you get a tailored LT-SPICE file with your parameters, everything inside. Many more things will come, like planar transformer design, or we also work on a full flyback converter end-to-end design, including the selection of IC controllers. Yeah, many more to come, and we will surely have webinars about this. And important to know, you have access to this tool at the moment because we're still in a testing phase, so you have free access by clicking the link. I assume Ellie will show in a second, or did already, or you got an email, I don't know that.
Okay, thank you, Jonas. I want to answer one of the questions because someone is asking, is a free version of a free trial? At this moment, this tool is free because it's version 3. So I'm going to share with everybody the link to register. And what I would like to share with everybody before starting the real webinar of Jonas is that this is not a finished tool. So this is going to be improved week by week. Jonas, when you want, you can start.
All right, let me start because we don't have so much time and I don't want to keep it within time that we organized. So I would like to talk about a new tool that we recently launched in Frenetic Magnetic Simulator. Again, Magnetic Simulator is our core tool. That's where we are strong at in designing and modeling magnetic components. And we introduced a new model that allows to calculate foil winding losses, and we use artificial intelligence for that. And I will quickly explain how this works and roughly high-level presentation about this. All right, so maybe first of all, why at all foil windings? This is a case we analyzed at some point. If you take round wires, but by kind of keeping the cross-sectional area and aligning them like this, you have much lower, or you have lower winding losses. So this is the promise of foil winding. This is because of skin effect, proximity effect. Basically, you have more skin around the wire, which helps you to reduce the losses. However, this is not always true. Often this is not the case. This plot is a bit complicated, but I will explain in a second. So if you have something like a foil with dimensions B and A, and foil, of course, is very thin, so it has a very low B, a high A, a long A, and you have an external magnetic field like this, and this field is parallel to the foil, which is, if the angle phi here is around 0 or around 180, then the theory from before is true. But if this angle here becomes more orthogonal to the foil winding, you have much higher losses, especially if you have A to B ratio very high, which is the case in foil. So you have much higher losses. This is something very typical in power electronics or in inductors of power electronics. Often you have an air gap, and if you have an air gap, you have a fringing field. This fringing field penetrates through the foils, and because of this, you have additional losses. And in this case, foil windings pretty quickly become worse than the solid round wires, but still there are use cases where foil windings are okay. And for us, it's not so important whether now you choose foil winding or not, but we need you to be able to model foil windings properly. This is why we implemented a new model for inductor foil winding cases that also includes the fringing field effect around the air gap. We discussed what kind of modeling approaches we should use. Basically, if you think of modeling magnetic components, you can have more like physics-based, Maxwell equation-based equations, or which are analytical approach equations, or some more numerical approaches like FEM or peak and so forth. You can also have empirical approaches. This is more used maybe in core loss calculations like Steinmetz or some correction factors and so forth, maybe a database. And the new way of doing this is advanced AI or machine learning. There are different algorithms, as you can see here. If you compare the pros and cons of the different approaches, I think one that leads to very accurate results is here, but you can see here the different, we quantified the different approaches according to different criteria, very accurate, very flexible, but not so fast. And what we need is something, because we design very quickly a lot of different magnetics, we need something that is maybe a bit less accurate, but very fast. That's why we chose AI, to approach it through AI, this problem. So what we did is we parameterized our case. We built a FEM, finite element model. We used the tool FEMM. It's an open source tool. You can use this, and build a lot of training data and a lot of test data. We use the training data then to train our machine learning model, and the test data to test our machine learning model. So in total, we generated around 5,000 foil geometrical setups, and we make sure that they are statistically well distributed. We computed then two-dimensional losses. We used, as I already mentioned, the tool FEMM. Many frequencies, small to big, and we simulated for around 3 weeks. So we had at the end a data set of around 50,000 rows. Here you see again the parameterization. We then analyzed this data. We did a bit of post-processing, something like, for instance, we took the logarithmic of the losses. Why we did this is that the losses are spread in more in a normal distribution, but more importantly, we have losses from very low values to very high values, and we wanted to compress them to have not too high order of magnitudes difference between the losses. As I already mentioned, we had a training and test set, and And we made sure that each feature is covered in training data as well as in test data. And we trained then a random forest regression algorithm. Training time was around 10 hours for this case. Random forest regression is a decision tree based algorithm, which is particularly good for tabular data as we have in our case. So we then also validated our approach, and you can see here the results. First of all, we have a medium relative error of around 9%, and 90% of the setups have less than 27% of error. So it's not perfect accurate, but for our purpose, it's accurate enough for the design of magnetic components. This is reasonable well. We also had to go from 2D to 3D, and in this step we lose another around 3%. So in total we had a median relative error of 12% of with our model. Now I would like to not just show boring data, but also a bit of a qualitative discussion of what actually affects the losses. So we analyzed different features we had, or the different we had, like how a model or how one situation or one case is determined, like the number of turns, frequency, and so forth. So basically all the things you can see here, plus the electric operating point. And you can see obviously number of turns has a high impact on the losses, the frequency has a high impact on the losses. But if you look through all these parts here, one thing that was quite some people were a bit shocked, or not shocked, but surprised, that the gap size has almost no impact. And also the temperature seems almost not to have an impact. So the question I have is, why does the air gap length has almost no impact on winding losses? And also for the temperature, it has an impact, but not so big. So before answering this question, I would like to go to a demo. So let me load the right here. Exactly, I prepared here a foil case. What I did is we designed an inductor with the following current waveform. So we enforce a fixed current like this with a particular core. And these are the winding losses. So we visualize foils at the moment as a block. So don't worry, these are the foils. There are 25 turns, 25 layers, because each layer has one turn. So it's one foil, no parallels, and the width is 5 millimeters. This is the width from here to here. Now, if I do the calculation, you see here that we have now AC losses, which includes all the winding losses of 0.63 watts in this particular case. Now, interesting, what I was claiming before is what happens if I change the air gap. So I change the air gap. For instance, I halve the air gap now. And I run it. And what you can see is the losses changed a little bit, but very little. And this is a bit counterintuitive, I would say. I will answer in a second why this is the case. Another thing that was a bit surprising is if I change the temperature. So now it was at 60 degrees. We have the winding losses, as I said before. I go now to 10 degrees temperature. So, I mean, this is the room temperature. That leads then to a lower winding surface temperature. If I run this, you see the temperature dropped significantly, but the winding losses only went down a little bit. So why is this the case? So I will go back to my short presentation. First of all, the question, why does the air gap length has almost no impact on the winding losses? Well, this depends a little bit on the assumptions I take, but one assumption I took is that the current is fixed. So I had a fixed current. I didn't change the current when I changed the gap. So if I change the gap, the reluctance of the air gap changes. But not only the reluctance changes in this inverse proportionally to the change of reluctance, I also have a different flux density. Right? It's like if I halve the air gap reluctance, I double the flux. But the product of these two quantities are the same. Now, what represents the product? It's the so-called magnetomotive force drop across an air gap. So this one stays the same, and this one is actually what determines your proximity losses due to the fringing field. Now, maybe that was a bit quick because the seminar is quite short. If you have questions, reach out to me. Happy to discuss this or provide you with more literature about this. Now, regarding the temperature on winding losses, the thing is, if you increase the temperature, you have a lower conductivity in your material, which leads to higher skin and DC losses, but also lower proximity losses. So that is not always balancing out, but in many cases, the losses remain more or less, or say more or less independent of the temperature. I think these are two effects that are very a bit surprising when we analyze the results, but if you investigate in the theory behind them, it becomes clear why this was the case. So that concludes my presentation. Our summary is, okay, we have this FEM approach, which is very precise but very slow, but we went for machine learning to imitate kind of the FEM results. Needs a lot of time for data generation, but this only once. It needs machine learning models training, but also only once. And it's okay, precise, it's not perfect, and it's super fast, so it helps us to design or compare many designs with each other. Okay, I think I was fast. I have to make the slides a bit bigger. Exactly, I forgot to do this. But anyway, I conclude now my presentation, so I'm happy to answer your questions.
Thank you, Jonas. We have some questions regarding engine and bring news. We have questions in the questions and answer part and in the chat. I don't know if you want to start with the questions and answer part of the application, or you want me to?
I can read them. Yeah. So the first question is: are you considering the foil always fill the winding window height? Not completely, but mostly. So we didn't go to half the window size. So it's a fixed factor that we introduced here. So it's a reasonable foil height compared to the core height. I hope I answered this question well enough. No, we did not yet train the model mixing foil and round wires. This is something we might do, we might also not do, and have more like a FEM approach integrated in our simulator for more complicated things. Then there is a question, is this a free version of a free trial? I don't know how to phrase this, but it's just that because it's in test phase, we give it out for free now, our Frenetic AI. But at some point we will change this, and then the people that have it will also need to go into a paid license. Yeah, but I hope I answered this question correctly.
Yeah, to understand better this a little bit, there is a normal confusion between these two tools. One is Frenetic Magnetic Simulator. This works with a paid license, and now we have Frenetic AI module. So this is free for now. So that's the link I have shared with everybody.
Yeah, that's very important. What I showed the tool today is Frenetic Magnetic Simulator. It's not a free tool. Reach out to us. We are happy to show it to you and make a presentation.
Yeah, the free one is only the tool you have shown at the beginning of the webinar.
Exactly, at the beginning I showed this. Now these were the questions in Q&A.
Yeah, let's go to the chat questions because we have a lot of.
There are some questions about over the course in the libraries. Yeah, so I can show, there were some questions about materials. So I can show this very quickly. If you go to, we have different material technologies, different manufacturers, and also different then materials behind, and also different core shapes. These are the very standard core shapes, including U cores and so forth. And these are standard sizes, but if you want to customize, you can also customize it, the dimensions, but you cannot do any random shape. Now, I think there are many questions in the chat. Somebody said he didn't or she didn't hear me. I don't know. I think most people.
Yeah, don't worry because
don't worry. I think, yeah.
Yeah, we have two questions about the what co-materials are loaded into the software. I think we have a previous one about the co-materials, so I don't know what that means.
Yeah, this is basically what I just showed. But I think the best is to reach out to us and we give you a demonstration and explain in more details. You can also add your own materials based on Steinmetz parameters. Now, I don't know where. Did you say you're working on an update to the tool to be able to model foils later? Well, the foils, well, for us, we have a kind of a B-field calculator. So model foils later. Well, this is basically what we did, right? We have foils. And if the air gap leads to a perpendicular field, but not exactly perpendicular, then we are able to model this. Insulation layers between foils, we have a little bit of insulation layer there, but at the moment we don't allow the user to adjust this. This is something we can change. Are you also modeling intertwining capacity? This is something we are working on now. So this is something we would like to include very soon. What is the maximum power rating that can be designed using the tool? This is a difficult question to answer, but it can go up to 100, 200 kilowatt. But I guess if you need a grid size transformer, we are not the right software for that. Did you say temperature does not affect winding losses, or does the core compensate for the winding losses on delta T? No, I didn't say the temperature does not affect winding losses. I said the temperature affects skin and proximity losses in one way and proximity losses in the other way, and together sometimes it balances it out. So it's not, yeah. So it does. Temperature obviously affects winding losses, but not always in the same way. How much will be the paid license? I think this is something we have to discuss afterwards.
Yeah, please. If you have questions regarding pricing, I'm going to share my email so you can contact me and we can calculate, because this depends on your needs, depending on the company, your needs, the number of people. So we can talk. Obviously, if you are attending the webinar, I will be great with you in terms of pricing.
Then maybe a few last questions. There was a question about PFC. Yes, we have PFC included in our Frenetic magnetic simulator. So that would be here. And we have it included also here in our Frenetic AI. Yeah. Okay.
Okay, we have time for two more questions.
Yeah, again, questions I have already answered. I read here.
Yeah, there's a question. Could you please explain again And this is a screen capture of your presentation.
Yeah.
I don't know if you have answered. What is the impact of temperature of winding losses?
Yeah, I can explain again. So what I showed is that the temperature has limited influence on the winding losses in this particular case. Very important. And why? If you increase the temperature, the conductivity of copper decreases. Okay, so generally you would assume higher losses. And this is true for DC losses, skin losses, but it's not true for proximity losses. Why? You have less eddy currents induced, and because of this, you have lower proximity losses. Now, it seems to be that these two effects, the lower proximity losses and the higher skin and DC losses, are balancing each other out. That's why in the case that we analyzed here, the losses were not so much impacted by the temperature. Yeah. Okay, I think we have to look a bit at time.
No, it's not. It's not open source tool. I'm reading the last question. It's not open source. It's a new creation.
Well, this FEMM that we use to train, although we might change now the tool to train data, is an open source tool. So yes, kind of true. Yeah, we use an open source tool to train. Our tool that is it's a different tool, right? It's not comparable to a FEM tool. It's a magnetic design suite that designs and models magnetic components with standard core shapes and core materials. So you cannot really compare these two tools.
Yeah, maybe it's a good. It's good to finish here, Jonas. And I'm thinking that maybe it's good to send everybody the recording next day with your slides, and also a link to some material regarding foil losses or other models.
Yeah, I have to find something first.
Yeah,
yeah,
let's see. We can.
Let's see. We have to see. Yeah, but we can share something.
Okay. So thank you everybody for connecting today. I will be in contact with everybody to send you the recording, and I have shared my personal email. So if you have any questions regarding pricing, regarding a private demo with our engineers, don't hesitate to contact. Have a nice day, everyone. Thank you, Jonas.
Thank you very much.
Bye-bye.
Bye-bye.